Lesson 3.3 Free fall. Imagine you have a ball and you threw it upwards. What are the forces? If we neglect air resistance, what are the force or forces acting on this ball? Would it be A, the force of your hand upwards, B, the force of gravity downwards, or is it C, both? Now the correct answer to this question is actually B, and let's try to understand why. Let's look at this example over here. You are standing at the top of a building. You have a ball in your hand, and you decide that you want to drop it from the top of this building. So what happens to the ball? It's gonna fall. It's gonna reach all the way to the bottom. So we can draw like a few instances here, like for example, the ball fell here, fell all the way down to here. So this is like around 3 seconds, around 6 seconds, and around 10 seconds it reached the ground. But I don't care about the time. What I care about is what are the forces or force acting on this ball at 3 seconds. And I'm going to tell you that the only force acting on this ball is gravity. Like we said earlier, gravity is the only force acting on this ball. Now, why is gravity the only force acting on this ball? Well, the main reason is that the only constant pulling force acting on this ball is gravity. If there wasn't gravity, the ball would simply just float. It would just stay where it is, since there's no force acting on it. But since gravity is constantly pulling it down, it'll eventually reach the ground, and that is the force pulling it. That is the force pulling the ball all the way down to the bottom. Now, I have another question for you. What if the ball was made out of iron? We had this iron ball. It's 100 kgs, and we decided to drop it. At the same time, we have this very, very light ball that's like 1 kgs, and we also drop it at the same exact time. So we have two balls. We have this ball in right hand and this ball in our left hand, and we both drop it, and we drop both of them at the same exact time. Which ball would land first? Now, the answer to this question is both. They will both land at the ground at the exact same time. So why is the question? And the answer to that is because gravity doesn't care about the weight. It doesn't care about how heavy an object is. It only cares about whether it is in the air and there's no forces acting against it. Since this ball is in the air and there's no forces pushing it back forward, the ball will simply fall at a standard rate of gravity's constant. The constant of gravity. Gravity's constant is 9.8 meters per second squared. And this is on Earth only. On the moon, for example, it would be something 2 meters per second squared. But on Earth, the ball would fall at a constant rate of 9.8 meters per second squared. The same thing with this one. It doesn't care about the exact weight of the ball. It only cares about whether it's in the air and there's no forces acting against it. Let's look at this example. Here we have a ball, and we're going to propel it forward, upwards, with a initial velocity of 20 meters per second. And the ball is going to go and follow this path, and then it's going to slow down and then eventually come back down to the exact same place where I threw it. So when you throw a ball upwards, it's going to come back down, obviously, right? So this is the exact same case, but let's look at it in a little more detail. So let's look at these 2 points over here. What are the forces acting on the ball at this point right here? Here we have obviously gravity, right? Going downwards. At all times, whenever the ball is in free fall, we have gravity going downwards. And then it's continuing to go, and then eventually it will reach this point where there's still gravity going downwards. And then the ball is going to come back down. I can't draw it exactly on top of each other, or else it wouldn't be clear. So I'm going to draw it next to it. But the ball is going to come down like this, the same exact acceleration, and again, the ball continues to go down until it reaches back to where it started. Now, gravity is a constant, right? 9.8 meters per second squared. But whenever we're solving, we want to make sure that we give it a vector. So we give it a direction. So gravity is always downwards, so we're going to consider it negative. So if any force is going up, we're going to consider it positive. If any force is going down, we're going to consider it negative in this example here. So we're going to, and we'll also round it up to 10 meters per second squared for simplicity. So this is the actual thing, but we're just going to make it 10 for easier calculations. So it started with initially 20 meters per second, right? So what we can do is, we know that it started with 20, and we want to know how fast it's going at this point right here. Well, if we know that there's always gravity, there's always the force of gravity accelerating it downwards, then obviously this number is going to change, and it's going to change by this magnitude. So what if we ask what is the velocity at this point right here, then we could say that after 1 second, the speed of the ball after 1 second is going to be having a vector of 10 meters per second upwards. Why is it 10? Because it was reduced, because gravity reduced the speed of this object by 10. And at the second of this ball traveling, it was reduced again, because there's always gravity pulling it down. So it's going to be reduced by another 10. So minus 10, it's going to be 0. Actually, let's consider this 30 meters per second. And we'll consider this 20. So 20 minus 10. And here the same thing, 20 minus 10. It's going to be, after 2 seconds, it's going to be 10 meters per second. Right, minus 10. And eventually we're going to reach this point over here. At 10 meters per second, it's going to be reduced again, and it's going to reach 0 meters per second at the 3rd second. Now, this point right here, where the object isn't moving, why is it not moving? Because the velocity is 0. This is a special point called the turning point, where the velocity of the object is 0. And what comes after the turning point is the ball is going to go down again. And it's going to go down by how much? Obviously, going to go down by 10 meters per second. So it's going to be reduced by 10 again. So 0 minus 10 is going to be, at the 4th second, it's going to be minus 10 meters per second. Now at the 5th second, it's going to be reduced again, and it's going to be minus 20. And then it's going to hit the ground at the 6th second at around minus 30 meters per second. So you can see here that as it started, the object is continuously being reduced by the force or the magnitude of gravity. Gravity's acceleration is constantly affecting the ball while it is in the air. And that is the free fall, where the only force acting on this object while it is in air is the force of gravity. And this is obviously always neglecting air resistance. Now let's look at some real-life problems that will come in the exams. So let's look at this simple example. It says there's a free fall ride. So this is like the ride over here. If you go inside of this ball, and shown. So this is a ride, and it starts from the top. So it's starting from here. At rest. What does at rest mean? It means that v initial is equal to 0. So initially starts at 0. And it becomes in free fall. So during some 1.5 seconds of this object falling, it is in free fall. So we have the time as well, 1.5 seconds. Okay, let's see what it asks us. So it's asking for the velocity. So v final. It's asking for the velocity at the end of the 1.5 seconds. So let me just make this more clear. So seconds. So v final. Asking for v final. So what do we know when an object is in free fall? We know that the gravitational force is the only force acting on it. So that means that the acceleration, or we can say g, is equal to minus 9.8 meters per second. Why is it minus? Because it's going downwards. The force of gravity is down. So let's look at some of the formulas, equations of motion. You should remember them. There's one more, but I don't think we'll use it here. And we want to know the final velocity. So we can take this equation here that gives us the v final, and we have the v initial, we have the acceleration, and we have the time. So v final, let's change color. V final is equal to v initial plus acceleration times time. V final, we don't know it, so we can just keep it as it is. V initial is 0 plus the negative acceleration, so minus 9.8, and then the time of 1.5. And then we can get v final is equal to negative 15 meters per second. What does this mean? That means that the object is moving, it reaches after 1.5 seconds of the object falling, it is going to be at an velocity, it is going to be at a velocity of minus 15 meters per second. That is how fast it is going to be going downwards. Now, part B here is asking for the distance. So delta y, how far do the people on the ride fall during this time? So during the 1.5 seconds, it wants to know how far it traveled. So first of all, we just calculated, since this question is related to each other, we just calculated the v final, which was minus 15 meters per second. And now we want delta y. Now we can use this formula, or this one. They both work. We'll use the first one. Delta y is equal to 1 over 2 vi plus v final times t. Now, we can just simply substitute, right? We have the v initial, 0, the v final, minus 15, and we have the time, which is 1.5 seconds. Now, this formula can be used when acceleration, or g, is unknown, but here we know that the object is in free fall. We can even use this one, or this one. We can use all of them. We have the acceleration, which is 9.8. We have the time, 1.5 seconds. We have vi, which is 0, so this cancels out, and it's going to be 0. So we have all the variables, so we can use any one we want. So when we use this one, we get minus 15 to 1.5, and then we get delta y is equal to negative 11 meters. This is how far the object traveled. It traveled 11 meters downwards. So exercise 2, a 500-gram stone. Immediately you see 500-gram stone, we can cross it out when solving for free fall. We don't care about mass right now. And it was launched vertically, so went up from the top of a hill, and it's 155 meters, like it shows here. And it reached the highest point. This is the highest point right here. It reached this point in 3 seconds. What do we know about this highest point? It's that this is also the turning point. So let's quickly write out what we know about the turning point. The turning point is A, 1, the highest point, and B, 2, the V is 0. So the V, the velocity at this point is actually 0 meters per second. That's very important when we want to find any question, really. So here it's asking for the initial velocity of the stone. What we can do is we can use the formula, which uses the initial velocity, this one right here, and relates the initial velocity with the final velocity. So what do we have given? We have v final, which is 0 meters per second, because it's the turning point. We have the time, which is 3 seconds. It says here 3 seconds. And then we have the acceleration, which is gravity, so 9.8 meters per second squared. And this is enough to solve this question. So 0, just plotting in this formula, I plus AT. Simply substitute 0 is equal to x plus, do minus 9.8. The minus goes here. And then t. Not t, sorry. 3. And then if we solve this, we get around 29.4 initial velocity. So VI, 9.4 meters per second. So that's the first part of this question. So part B here, the next part, it's going to ask us for the total time that stone spent in the air. So it wants to know how far it's spent during the air during its entire duration. Now it gets a little tricky here, but it's pretty easy. So first of all, we need to find the total displacement. So it told us the displacement for just this part here. So just this part of the journey. We don't know how high this part of the journey is. So we need to find that first. So how do we find that? Well, we have the V initial, which we just calculated, 29.4 meters per second. We have the V final, 0 meters per second. And then we have acceleration, which is 9.8 seconds squared. And then we have the time, just 3 seconds. And then we can simply calculate it using any of these formulas. Delta y is equal to VI, so 29.4 into T, just 3, plus, we'll do minus, just take this minus, put it here, 1 over 2, 9.8, and then T squared, so 3 squared. This way we can calculate the delta y. It's going to be around 44 meters. Now, knowing this, what we can do is we can add this to the total displacement. So it's going to be 155. Here's 44. So now our total delta y is going to be equal to 199 meters. And we can just use this exact same formula again. Let's just write what our given is for just this part here, right? We already know the time for this part. So from A to B, so this part of this journey is 3 seconds. And we want to find the journey from B to C. So from A to B, 3 seconds, and then B to C, we're going to find it, and then we're going to add them, and that's the total time. So from B to C, what do we know? We know that the V initial is 0. Why is it 0? Because this is the turning point. So if we start from here, then the V initial is 0. We know that the acceleration is minus 9.8. And then we also know that delta y is 199 meters. And then we can use the formula, which is 199 is equal to 0. So this can immediately cross out, because this gives us 0, Vi times t. So it's 0 minus 1 over 2. I'm going to take the minus again, put it here instead of next to the 9.8, just easier. And then times t squared. Now, all we need to do is use a calculator, and the answer is going to be 6.3 seconds. Now, all you have to do now is add the total. Remember, it's asking for the total time spent during the entire journey, so you're going to have to add it. It's going to be 9.3 seconds. And that is your answer. That'll be it for lesson 3.3 freefall. If you have any questions or want to ask anything at all, you can ask it down below in the comment section or in the server. I highly suggest that you revise and you solve as many questions as possible, because physics requires practice. That'll be it. Good luck.